So before we get going here today, we've got that Excel assignment, individual assignment that's due at the end of the week. Kind of get going on it. It'll be very similar. So when we're talking about a normally distributed variable, it's going to be pretty similar to what we did here on this temperature worksheet of that Indiana weather data file. And then the log normal stuff is going to be what you can kind of find in this rain worksheet. And this, I put this up on Canvas. I think it's called, there's Indiana weather blank and there's Indiana weather in class or completed. I forget exactly what I called it, but it's all the work that we did in class. Now, the very first question asks you about what does your distribution look like? So I'll show you a really easy way to do this. So let's say we had this November rainfall. So I would just select that entire variable, right, the entire column of data in a really good way. I'm not expecting you to put a lot of work into, maybe creating a histogram based off of kind of different bin widths. Here we can kind of use this built-in tool, which I told you not to use a long time ago because I want you to learn how to use these functions, but at least to get a quick idea about what this distribution looks like, you can use this statistics or this histogram option where it's just inserting this table. So I'll insert this histogram. This kind of shows me that this variable, kind of a normal distributed variable, but if I had to say here, I'd probably say this has a little bit of a right skew to it, right? Now, depending on your variable, you might end up with something that looks like none of the distributions that we've talked about, right? So we kind of had this exponential, which we said looks something kind of like this, right? Where there was almost no left tail. We had, so this is kind of exponential, log normal, looks something like this, which we kind of had, looks like a really right skew distribution. So if I'm saying this probably looks maybe log normal, right? Or it's just got kind of a right skew to it. Either way, I'll be okay with that. And then if you end up with a variable that kind of looks pretty symmetric, where the bulk of the observations are in the middle there, we would say that would be kind of a normal distribution. You could end up with another one, which is, I just don't expect anyone to, although I forget exactly every topic everyone has. But if you saw something that was pretty even, this would be a what? Do you remember what this distribution was? Uniform, right? Where everything was equally as likely. Like I said, I doubt too many of you will have a variable that looks like this, but it is a possibility, right? So those are the distributions we've talked about: exponential, log normal, normal, uniform. If yours doesn't match up with any of those, you can state kind of, it doesn't look like any of the distributions that we've talked about. Okay? Or kind of say which one it looks the most like, okay? Does that help kind of clarify a little bit? Okay. If you have questions as you're working on that, I'll be in my office today from 2 to 4, as well as tomorrow from 2 to 4. If those times don't work for you, send me an email. I'll be around most of the day tomorrow. So just making sure that I'm in my office. We can kind of set up a time outside of that 2 to 4 time frame to kind of meet. Okay. Other questions? Also, I'll mention Friday. It might be around Friday afternoon a little bit as well. Well, I know I'll be around. I might have some time where you can stop by Friday, and I'll mention that on Friday as well. Okay. All right. Any questions before we kind of jump into the material here today? Okay. So, starting to get to some interesting stuff here. So we've talked about all these distributions, right? I've got them listed a couple of them here. One thing that I don't know if I inherently said as we were going through this, but if you go back, you kind of recognize that I was using this notation for the standard deviation, which kind of reflects that we were, with all these distributions, talking about the original population data. Now, we often, like we talked about last class, we don't have population data. We have to get a sample, and we want to try to do all these things that we talked about last class to make sure our sample isn't biased and that we're getting a sample that reflects the population. Right? So what happens if we only have a sample, right? Because now I might not know that my district or my variable is normally distributed, right? I can't observe the population data, but we're going to end up finding out some things about the distribution of our sample data, right? That helps us make some pretty powerful statements, okay? So if we think about this, let's use income as the example. So let's just assume for a second that we start out with this variable income and it's normally distributed, okay? So you can kind of think about what are the range of possible values that I could see for this normally distributed variable X. Well, you know, probably the majority of people make, I don't know, I think it's actually closer to 55, but like the average income is about 50,000, you know, but I could still see people maybe that only make 10,000. I could also see people way over here that, you know, I don't know, make 500,000, right? If I instead look at the distribution of my sample means, right, think about what that's going to look like. So I could go out, this is my population data. I could go out and randomly sample, say, 100 people, calculate that sample mean, write that down. Go out and randomly sample another 100 people, calculate the sample mean, write that down. I can kind of continue to do this until I build a pretty big data set where I maybe have like 1,000 sample means. Well, once I have 1,000 sample means, just like I showed you kind of using that built-in histogram tool in Excel, I could quickly get an idea about what the distribution looks like for my sample means. All right, if I take enough samples, I basically just got a data set where it's not a random variable X, it's a column of data that represents all these different sample means that I took. And if I graph those, I can get an idea about what the distribution of my sample means look like, okay? So, okay. So the sample mean has its own distribution, right? And just to kind of think about this a little bit, in respect to income, if I select one person at random, I could see that they make $500,000. If I select 100 people at random, what's the likelihood I see that the average income is $500,000 across 100 random people? Pretty small, right? Any one person may have these extreme values, but when I'm looking at 100 people, it's very unlikely I get 100 people who are making values that are very far from the mean. So what ends up being true about our sample mean distribution is it's a little bit tighter, right? Or you can kind of think about it as the variance of my sample means is going to be a lot lower than whatever the original variance of the data was, right? Because I can't see these extremely large values. The other example I always use is height. So when you think about, you just take one person at random, maybe they end up being 7 foot tall. If I take a random sample of 100 people, what's the probability that the average height is 7 feet across all 100 people? Almost zero, right? And so if I'm taking these samples, I'm going to get kind of this tighter distribution, or this distribution that has a lower variance, right? The values that I'll see for my sample means should be more likely to be around whatever that true population mean is. Okay. Now, for now, I'll kind of go through this and I'll kind of tell you this, but we'll eventually kind of use some data to prove this is the case. But what ends up being true is that the mean of my sample means ends up being exactly whatever the mean of the original data was that I was sampling from, okay? So we can take these samples of different sizes. Remember, lowercase n kind of representing my sample size. What do those distributions look like? What do those distributions look like? What's going to end up being true, as long as we have one condition met, is that my sample means will also be normally distributed, right? The mean of those sample means, I remember I was talking about I take 1,000 different samples, calculate the sample mean, put that in a column of data, right? Those sample means will have a mean that is exactly equal to whatever the mean of the data was that I sampled from. Okay? What also ends up being true, and this isn't quite as intuitive, but this follows from the idea that I was talking about, the standard deviation of my sample means is lower. It's not as likely I see these extreme values when I'm looking over 100 people. So the standard deviation, or the variance, I guess it's like we can talk about either one, right? But the variance of my sample means is just the variance of the original data we sampled from divided by how big my sample size is. So the reason why this is the case is if my sample size gets larger, what's happening to that variance of my sample means? Well, farther and farther away, but it's getting smaller, right? Well, my denominator gets larger, the fraction as a whole is going to get smaller, right? So as I take higher sample sizes, I know the variance of those sample means of whatever that sample size is will get smaller. So this is the idea that if I was taking random samples of 2 people, well, if I take random samples of 2 people, think about the income example, maybe I do get people on this side of the distribution. So it's still fairly likely I see the average be 250,000, 300,000. If I take 100 as my sample size and I did 100 random people, it's very unlikely I see 200, 300,000 be the average sample mean, right? So that's the idea that as the sample size goes up, that variance of my sample means is getting smaller and smaller. It's more likely that in my sample of a larger sample size, I'm getting a value that's pretty close to the mean. I can actually take this out a little bit further. Maybe this will help make a little sense. So let's say I've got this population data. If I took my sample size was the entire population, what's my sample mean going to be? If I've got every single person in the population, my sample is the same size as the population, my sample mean will be whatever the population mean is, right? So if I could take a sample size high enough, I would always see, if I had the population data and I sampled that amount of people, like let's say I was thinking about the income in the US, and I literally took everyone in the US, well, every random sample is going to be everybody in the US. I'm always going to get the exact same value for that income. So if my sample size was the population, my variance would literally be 0, right? Every single sample would have everybody in the population. So as we get these higher sample sizes, I can drive that variance down. And that's going to have some pretty useful implications for us. So this is kind of where I start to kind of hammer this idea home that higher sample sizes are always a better thing. Almost always a better thing. Right? For the sake of this class, it'll probably, anything we talk about, it'll be always be better to have a higher sample size. Okay. So that's kind of me just telling you some things about the distribution of the sample means. I'll eventually prove to you with some data today that these things will actually hold. Okay. But I think the intuition behind this idea that the mean of my sample means is whatever the mean of the original data was, and that the variance of my sample means is getting smaller. It's the original variance, but divided by how large I'm taking the sample, right? Or how large my sample size is. Fairly intuitive. Kind of already mentioned this. What are the 2 things that influence the variance of my sample means? Well, if I take a higher sample size, it drives it down. But also, if the original data has a higher variance, then my sample means distribution will have a higher variance, right? This is the idea, income, I could see anything from 0 to whatever Jeff Bezos makes, right? It's going to be a pretty large variance in my sample means as well. But if I'm looking at, height data, where I know it's in a much smaller range of values, well, then the distribution of my sample means for height is going to be much smaller, right? So these 2 things kind of influence that variance of our sample means. And then the standard deviation, once again, we just have the square root. So here I want to make this point because the mathematics will sometimes see things written a little bit differently. So if I'm thinking about the standard deviation of my sample means, I can write this out, right? I just take the variance of my sample means and take the square root. Right? But taking the square root of something that's squared, I can actually also write this out as simply the standard deviation of the original data divided by the square root of my sample size. So we'll see this written out in 2 ways, and the reason why is because sometimes we'll have the variance of the original data we're sampling from, sometimes we'll only have the standard deviation. Depending on which one we have, one of these kind of equations might be a little bit easier to work with. So, and don't worry about this, I'll talk about this here in a second, but we need to make sure that we actually don't have too large of a sample size in respect to our population. If we ever did, then it's probably better, like if we get close enough to our population where our sample size times 20 is greater than our population, we probably should just do the work to get the entire population data. But I'll never try to do this. Almost every situation, we'll never be able to get a sample size this large. So it's not that big a deal. So let's put some actual numbers to this and kind of start to visualize what's going on here. So let's say I've got, I think this is birth data. Yeah. So let's say I've got some birth data. And the original population data, I can see that the average birth weight is 3,287, and the variance on that birth weight is 360,000, right? So what I'm thinking about here is I've got this normally distributed variable, which is birth weight, one of these biological kind of metrics that happen to be pretty normally distributed. And I've got this variance of 360,000. Okay. What's going to be true is that when I'm thinking about the distribution of my sample means, let's say I have this entire data set and I start sampling 36 births from it, calculating the sample mean, writing that down. Randomly sample another 36 births, calculate the sample mean birth weight, write that number down. I continue to do this until I have a really big data set, maybe 1,000 different sample means. I then graph what that distribution looks like. What ends up being true is that distribution will be normally distributed. The mean of those sample means will be exactly equal to whatever the population mean was. And the way I drew this doesn't kind of necessarily show this, but if I'm thinking about the variance of my sample means, that should be, here, kind of write this out. Not thinking about the standard deviation, should be the original variance divided by, I think this is 1,000 if I'm looking at this right? No, it's not, it's 10,000, isn't it? Right, divided by whatever my sample size is. Okay, so here I'm taking 36 births, that's my random sample, my sample size is 36. So my mean of my sample mean should just be the mean of the original data, 3,287. So I know it's either the A or C. And then from there, what's the standard deviation? Well, if I had the variance was 10,000, the standard deviation should just be the square root of that, or 100. Okay. Any questions on that before we keep moving here? Like I said, for now, just accept these things as true. I'll kind of prove it to you with data here in just a second. We go through the proof, but it's not overly interesting. We could do this for different sample sizes as well. So I just wanted to make the point here. If I, instead of 36, took sample sizes of 100, what's going to change? So if I'm drawing out this distribution, it's going to have what's going to be the mean of my sample means if I take samples of size 100. Going to be the same, right? The mean of my sample means is always whatever the original mean of the data I sampled from was. So it's going to be centered around the same point. But what's going to happen to the variance or the standard deviation of my sample means? If I take a higher sample size, what's going to happen to the variance of the standard deviation? It's going to be smaller, which we talked about a while ago. But if my variance gets smaller, what happens to my distribution? A smaller variance means values further from the mean are less likely, and values around the mean are going to be more likely. Right? So you can kind of think about this as like, I don't know, we'll call this, if we're trying to take notes, distribution 2, right? When I take samples of size 100, they're still going to be centered around that same population mean, but that variance is going to be smaller, so I get a tighter distribution, or a more peaked distribution, where the values near the mean are more likely, values further from the mean, less likely. So you can kind of imagine, why is this a good thing? Well, because if I can only rely on sample data, I want to make sure that the sample mean I'm seeing is as close to that population mean. Well, if I can take higher and higher sample sizes, I'm making it more likely that I'm seeing a sample mean that's really close to whatever that true population mean is, and less likely that I'm seeing values further from that mean. The idea that if I just take a random sample of 2 people, hell, my average income could be way off of what the true average income is. If I've got 1,000 people Well, that sample mean income is probably going to be pretty close to whatever the average income in the U.S., across the population is, right? So here's the idea that, larger sample sizes are always going to be a good thing. If I know it's driving down my variance or driving down my standard deviation, and before my standard deviation was 100, which of these has to be the correct answer? C, right? So my variance has to be lower when I take a higher sample size because I'm making the denominator larger. So if before the standard deviation was 100, I know it has to be lower, so it can't be 600, right? It has to be 60. And then from there, it's also centered around that same value. That hasn't changed. The mean of my sample mean will always be whatever that original population mean was. Okay? Any questions on that? Going through this a little bit quick. I've already kind of mentioned this. I don't know. Once again, I still think this from the book. I don't actually love this one. I should probably do it. But it does, I don't know. Maybe it's good. Here's the original population data. If I were to take samples of size 5, notice my distribution is getting a little bit tighter. If I then kind of take distributions of size 50, well, now I'm getting this really low variance, right? By increasing that sample size, I'm getting this really tight distribution, right? So more observations, the better. That's the kind of summary there. I could kind of do this from a random number generator. So I have this population data where the sample size is 1. Sample size is 1. I'm just randomly selecting one person. It's literally going to look like my population data distribution. So here I try to kind of have this uniform distribution. So notice it's like every outcome was kind of equally as likely. There's a little bit of variance there because I was randomly sampling one, but pretty close to a normal distribution, or sorry, uniform distribution. And then as I take sample sizes that are higher and higher, notice these distributions start looking. So here's some of the sample size of 5, sample size of 3, sample size of 50. As I get higher sample sizes, they start to look closer and closer to a normal distribution. Okay? Even though the original data started out as a uniform distribution. Okay? So how can I guarantee that my sample means, so I've already told you the mean of my sample means will always be the mean of the original data. So n equals 1 was the original data. Notice this mean, these distributions of different sample sizes are all centered around that same value. Now the variance of those distributions is changing. As they get a higher and higher sample size, notice it becomes a lot more peaked, which should reflect that it's getting a lower and lower variance. Okay? Excuse me. But how can I guarantee also that my sample means are normally distributed? That's how I was drawing them out, but there's no reason for you to believe that that's going to be the case, okay? But what ends up being true is that, here, I'll skip ahead of here. I'll come back. As long as we can get a sample size over 30, the central limit theorem allows us to mathematically prove that the distribution of my sample means will be normally distributed. As long as I can get a sample size over 30. So notice here, 1, 3, and 10, these are close to a normal, but not great, right? Once I get to 50, this is almost like a perfect normal distribution. So as long as I can get a sample size over 30, I know that my sample means will be normally distributed. Why is that helpful? Because if I know that my sample means are normally distributed, I get the sample size over 30, well, I know the mean of my sample means is whatever the original mean of the population data was. And I know that the variance of my sample means will be whatever the original variance was divided by my sample size. Well, once I have those two things, I know it's normally distributed, I can convert this into a standard normal distribution and think about what's the probability that in my sample, I see a value above or below a certain value or between two values, right? We can kind of do all the old stuff that we were doing, right? So if we can guarantee that our sample means have a normal distribution, which is getting a sample size over 30, we can go back to doing all the stuff that we were doing before. Right? By converting that normal distribution to a standard normal, using that standard normal distribution with our z tables to find these different probabilities. Okay. And kind of to mention here, having a sample size over 30 is great. The higher and higher we take, the higher and higher sample size we take, the closer it gets to a normal distribution. So over 30, it's a close enough approximation that we can treat it like it's a normal distribution. But if we continue to take higher sample sizes, it's going to become an even closer approximation allowing us to kind of be even more precise. Yeah.
So are you saying that no matter how X is distributed, do you mean that like so we're looking at the board? You're talking about the top graph. It doesn't matter if that's
doesn't matter how it's distributed. So in fact, I think here, I'm just saying, it's coming up. This is a good question, right? So it doesn't matter what my original X variable starts out as. It could be uniform, it could be kind of exponential. I don't even know what the hell this is, right? It's a linear, and then we've got kind of this parabolic kind of shape. It doesn't matter what the original variable is kind of distributed as. As I take higher and higher sample sizes, notice that a sample size of 2, I mean, I got like a ghost-looking distribution here. It doesn't have to be anything, right? But as soon as, 6, okay, they're starting to get pretty close to normal. Some of them are still skewed quite a bit, right? But it doesn't matter what the original distribution is. If I can get a sample size of 30, notice all of these are normally distributed, right? They're kind of centered around that original population mean. They're symmetric. And you'll notice they're really peaked, right? We're getting a pretty tight distribution there. Okay. That's what you're asking, right? Yeah. Yeah, so it doesn't matter, which is great, right? So I think I've got, I don't know. I'll skip ahead here because I think I'm making this point. I think I have a great meme here. We'll see if it's true. Right, so assign you all these different, right? Part of the individual assignment, right? You've got to do log normal distributions. We've talked about all these distributions. And then I tell you that, like, okay, central limit theorem makes all this irrelevant, right? Because if we take samples of size 30, who the hell cares what the original variable was distributed as? We now know that our sample means will be normally distributed. Okay. Also, does anybody know what this is from? Yeah, you should all watch this movie. It's hilarious. The room really ties, or the rug really ties the room together. So, anyways, go out and watch that very funny old movie. But now I'm going to prove to you that this is true. Right? It doesn't matter what the original variable started out as. Our sample mean should be normally distributed. Okay. So I've got all this old birth data, right? And I've got different variables. So birth weight, length of the pregnancy or gestation, Apgar score, which is kind of like a measure of health of the infant once it's born. They do very quickly. And then whether or not the mother smoked while pregnant. This is going to be somewhat alarming. It's older data, 2004, but we'll talk about this in a second. Okay? So if I have the population data, right, all 87,000 births, right, I can calculate pretty easy in Excel the means and the standard deviations. It's pretty easy. We've done that. You can kind of see, birth weight, length of pregnancy, whether or not they use tobacco, and then kind of this Apgar score, which is a 0 to 10 measure. Okay, so I could calculate these ahead of time. Now, the most alarming thing is still 18% of mothers kind of had nicotine in their system while they were pregnant, which, like I said, this is 2004, so hopefully this has changed, but a lot higher than I thought it would be. Anyway, so we've got these original means, these standard deviations. If I were to take samples from this data and then graph what the distribution of those sample means look like, hopefully the mean of my sample means should all be centered around the population mean values, and my standard deviations of my sample mean should be the original standard deviations divided by the square root of n, or the square root of my sample size. So what I'm going to do is first look at the population data, and then we'll talk about the process that we would do to get our samples and look at the distribution of our sample means. So here's birth weight, pretty normally distributed. Once again, one of these biological metrics happens to just be normally distributed. Okay. It's obviously got like premature births where infants are very, very small. Not as many really fat babies, I guess, on the right side. So maybe a little bit of a less skew there, right? If we look at the length of the pregnancy, I think I showed you this example a long time ago. Definitely has a left skew. We see premature birth. We don't see babies being born at 11 months, right? So we've got kind of a normally distributed variable, a left skewed distribution. The health variable, almost all babies are given a 9. There's a few that aren't, kind of, who are unhealthy when they're born, kind of receiving lower scores. This is, a left skewed distribution, but it's not even continuous. I'm going to make an interesting point here that even if the original variable we're starting out with isn't continuous, our sample means will be. So think about it this way. The most extreme would be, I didn't provide a graph here, but if I had my maternal smoking variable, what would the graph look like? It'd be 82%, we saw 0, and then 18% percent we saw that they were, right? It's just a binary variable. But when I take a sample, if I take like 100 random births and then I calculate what was the average of mothers who smoked, well, I'll have ones and zeros. I could see anything in between these two values, right? Think about if I just had a sample size of 2. One of the mothers smokes and one doesn't. My sample mean would be 0.5. Right? If I have 10 people, one of them smokes, 9 of them don't. My sample mean is 0.1. So even if the original variable starts out as not continuous, my sample means, if I take samples of different size, I can see any decimal value in between 0 and 1. So my sample means will be continuous. So if what I'm telling you is true, even this maternal smoking variable, once we start to take samples, the distribution of our sample means should be normally distributed. Okay? They should be centered around the original population means, and the standard deviation should be the original standard deviations divided by the square root of our sample size. So I think what I did was I took samples of size 100, to make this easy. Because if I take the square root of 100, that's just what? 10? So dividing the original standard deviations by 10, all my standard deviations should just, the decimal should be moving one place, right? That's just easy to think about. Now, it doesn't have to be 100. It just makes it a little bit harder to see if I take different sample sizes that it's still going to follow the same rule. But with a sample size of 100, we're just going to be seeing that decimal point move 1. So it's kind of a nice sample size to take. So I randomly selected 100 births from this population data, wrote that number down, right? Took another random sample of 100 births, calculated the means of all these variables, wrote those down, kind of continued to do this until I had a data set where I had like, how many did I do? 1,000 different sample means for each of these 4 variables. Now, all these random samples were of size 100. I have to keep the sample size the same. But once I have these 1,000 sample means, I could use that like built-in tool to get a really quick, easy idea about what does this distribution look like. If I didn't use a built-in tool, I created actual histograms where I kind of put the bin widths what I wanted. But we can kind of take a look at this. Okay? So this is from actual data, right? Here was the original population mean, the original population standard deviation. My new kind of my sample means, the mean of my sample means should be the original population means, and the standard deviation of my sample means should be the original standard deviations divided by the square root of 100 or divided by 10. So those standard deviations, we should be seeing that decimal point move one place. Okay. Actually, I think it's wrong. One place, go the other way. Sure enough, right? It's a little bit off. I've only got 1,000 sample means. Technically, to prove this to you, without a shadow of a doubt, I would have to have like an infinite number of sample means. And in terms of the mathematical theory, we can't really do that. But the theory is hard to understand. Like the mathematical proof is hard to understand than just having data. And I think even with 1,000 samples, we can kind of see, oh yeah, the mean of my sample means very close to whatever the original population mean was. Right? I mean, these are off at like the second, these aren't even off at all. I mean, they might be out to like the 4th or 5th decimal, right? We're basically getting that the mean of our sample means is always whatever the original mean of that population data we sampled from. And the standard deviation, once again, our decimal point is just moving one place, divided by the square root of 100 or divided by 10. Now, it's off a little bit because I'm rounding here, but you know, like this should technically be 0.266. If I kept this out of 3 or 4 decimals, it was a lot closer than being off by 0.04. But even if it was, right, it's not being off by much for only having 1,000 of these sample means. To really prove the theory, like I said, I would have to have like an infinite number of sample means here, or hundreds of thousands, right? But even a quick kind of demonstration with 1,000 sample means, we can see that what I was saying is kind of holding true. Okay. Any questions on this idea? Okay, so what I also told you was that as long as we have sample sizes over 30, these sample means should be normally distributed. Here, I've just shown you that at least what I was telling you about the mean and the standard deviation is holding true. Right? But we actually can see that even for these variables that start out that aren't continuous, like the maternal smoking variable is just 0, 1, we get a normal distribution for our sample means. So here's the distribution of all these 1,000 sample means for birth weight. I mean, this is a perfect normal distribution. But kind of the point I wanted to make with this is, so the original variable birth weight was normally distributed. If we go back oops, right? Here was our original population data. Well, I could see birth weights up in the 5,000s, also as low as kind of under 1,000. Well, once I take 100 random births, the values that I could see for those sample means, we said there should be a tighter distribution. So notice, there we go. For my sample means, I'm never seeing values above 3,500 or below 3,000, right? Because if I select any one birth, yeah, I could see really small or really large values for birth weight, but if I've got 100 random births, the average or the sample mean of those 100 is way more likely to be a value that's really close to whatever that population mean is.
Is that almost like getting rid of an outline?
Yeah, it's the idea of even if I have an outlier in my sample, because I have more observations, excuse me, when I'm calculating a sample mean, we said it's kind of like this, where you can kind of think about it as a weighted mean, but everything's being equally weighted. Well, if I take a higher and higher sample size, any one observation has a smaller weight. So even an outlier won't impact that sample mean near as much. So taking higher and higher samples, it's going to guarantee that even if we end up with an outlier in our data, right, or in our sample, it's not going to skew our mean near as much, which is why when we look at the sample mean values, we see things that are a lot closer to whatever that true population mean is. Is that kind of... And then we kind of look at these other variables. So remember the original variable of the length of the pregnancy started out as left skewed. Now our sample means for that variable, nice normal distribution. We're not seeing extreme values. In fact, it's like limited between what, 39.5 and 37.5. We're getting a really tight distribution here. The APGAR score, once again, maybe it's something a little bit kind of goofy going on here with the right side. If I took samples of larger sizes, this should get closer and closer to an approximation for a normal distribution. But even here, I would argue this is pretty close to a normal. And then maternal smoking, which is the weird one, I didn't show you a graphic that was just this 0-1. Notice for our sample means, we get this kind of nice normal distribution as well, centered around that 0.18 population mean. So even if we start out with a variable that's not even continuous, binary, in fact, right? Our sample means will be normally distributed. They'll be centered around whatever that original population mean was, and the variance or the standard deviation will follow this idea that it's the original variance divided by the sample size. Questions on this? Keep moving here. So I don't know. I'll start doing more of this as we cover material because I haven't done this in a long time. Mathematical proofs just suck. I mean they're really hard. I mean they're interesting, but they're very difficult. But I always even when I'm doing some of my own research stuff, if I forget what the theory is exactly, I prove it to myself using data, right? If I can't remember that the standard deviation of my sample means is the original population standard deviation divided by, well, I can prove it to myself with data. It's way less likely it can actually work out that mathematical proof from memory, right? But I can prove to myself that that's going to hold with data. So I like to kind of show examples like this, especially since don't really want to go through the mathematical proofs with you guys. So that's kind of where we're at with that. We're out of time. Okay, so how do we want to end today? So I think we'll kind of introduce this idea. We'll work through more examples next class. But let's say I start out, I take a sample, right? And I might want to figure out, okay, what's the likelihood if I sampled 100 people that I see a sample mean income value that's, I don't know, below 35,000? Well, I know my sample means are normally distributed as long as that central limit theorem applies. So if I get a sample size over 30, I know that my sample means should be normally distributed. The mean of my sample means should be whatever the original population mean was. And the variance of my sample means will be the original variance of the data that I sampled from divided by my sample size. Well, now that I have this normally distributed variable, I can convert it into a standard normal distribution. So just kind of a reminder, how did we do that before when we had population data? I did that, right? If I'm creating z-scores for sample mean values, or z values for these sample means, I'm no longer interested in cutoff values for X. I'm interested in cutoff values for my sample mean, right? So I'll take whatever that cutoff sample mean value is. I'll subtract the mean of my distribution. Well, I'm no longer looking at the population data. I'm looking at sample means. So the mean of my sample means, well, this is kind of nice, right? So I've got to subtract the mean of my sample means. But the mean of my sample means is just the original population mean. I'll then divide by, excuse me, the standard deviation of my sample means, right? So we're no longer looking at the original population data. We're now looking at the distribution of my sample means. So when I subtract the mean and divide by the standard deviation, it needs to be the mean and the standard deviation of the variable I'm looking at. The variable I'm looking at is now the sample mean. However, I know that the standard deviation of my sample means I can rewrite this as the square root of the original population variance divided by my sample size. So I'm still following the same rules to calculate my z-values or my z-scores. It's just that now, to find the standard deviation of my sample means, I've got a little bit more work to do. Right? Now, the mean of my sample means, that's pretty easy. But you know, things change a little bit when I'm looking at that standard deviation of my sample means because it depends on my sample size. So once I convert this into a standard normal distribution, I can write that z-score equation looking like this. This is, once again, where I'll kind of always show you both ways, right? Here I wrote that as the square root of the variance over the sample size, the square root of something squared. I could write that as just the standard deviation divided by the square root of my sample size, right? Two different ways of kind of writing that z-score equation for my sample means. Once I do that, I think about what region am I looking at. Once again, drawing this out will kind of help us not make easy mistakes. Also think about what we're looking for. And then if I ever want to, you know, the probability maybe of being greater than, I'd have to do 1 minus, or I might have kind of this fourth step, which is once I have these relevant probabilities, I might have to transform them, right? I might have to subtract them from 1, or if I want the probability of being in between two values, subtract the smaller from the larger, kind of all these same things that we talked about before, right? So really the only added step here is we have to know that the variance of our sample mean is the original population variance of our sample size, which complicates or changes our z-score formula a little bit, right? But once we have that z-value, it's the exact same process we were doing before. Look that z-value up in the table, and then kind of use those probabilities to find whatever that region that you're looking for is. Any questions on the... I think we'll work through an example here, and then I think I've got one thing I'll show you. So we'll leave this up here. Let's say I've got an example like this. So I've got some normally distributed variable that has a population mean of 5, a population variance of 2,500, and I take samples of size 100, and I want to know what's the probability that I see my sample mean be between 10 and 15. Okay. So I'm going to start drawing this out. I've got a sample size over 30, so I know my sample means should be normally distributed. Right? They should be centered around what value? Well, the mean of my sample means is always whatever the original population mean was from the data, or from the data I sampled from. What was the original variable that I sampled from? It's X variable. It had a population mean of 5. So my sample mean should be centered around that same value. What's the, excuse me, standard deviation of these sample means? Well, it'll be the original variance, which is what, 2,500, divided by that sample size of 100, which I believe I chose these numbers to be nice and easy, so that we end up with a standard deviation for my sample means that's also 5. Okay. I then said, okay, what's the probability that I see this value for my sample mean be somewhere in between 10 and 15? Okay. So I take this sample, you know, maybe I mentioned like, man, this sample mean seems kind of high or kind of a little bit off, but maybe it's not that unlikely that from my sample, I saw a sample mean value as high as, you know, somewhere between 10 and 15. So if I can, how can I figure out what that probability is? Well, I've got a normally distributed variable. I can turn it into a standard normal distribution. What would the z-score for my mean be? So we said the z-score interpretation is the number of standard deviations away from the mean. So yeah, the mean should always have a z-score of 0. Right? From there, I need to convert these two values of 10 and 15 into z-values. Now, I have the equation up here. I can go ahead and plug all my numbers in. But if I calculate these intermediate steps, notice if my standard deviation of my sample means is 5, the mean is 5, and I'm looking at the value of 10, how many standard deviations away would 10 be from 5? Yeah, it's 5 away. The standard deviation is 5, so it's 1 standard deviation. Now, I can plug all those values in and prove that to myself. But when the numbers are kind of work out nice like this, it's sometimes easy to envision how many standard deviations away we are. If I then think about 15, well, that's 10 away from the mean. My standard deviation is 5. So how many standard deviations away should I be? Or what should my z-value be? 2. Right. So I can go ahead and plug those numbers in if I really want to read, if I had harder values, right? If I didn't have kind of these nice integer values. But basically, I convert these two values into z-scores. Okay. Once I have those z-scores, I can look up that z-value of 1 on my table. The table gives me the area to the left. I could then look up that z-value of 2 on the table. The table will give me the area to the left. The final step that I would have, subtract that smaller probability from the larger probability, and I've got kind of the area in between, right, or the probability in between those two. So we literally worked through a problem where we had these exact same z-values. I don't know if it was last class or the early class before that, right? We go to the table, skip ahead here, and look those up. We can find those probabilities pretty easily, subtract those two from each other. Oh, there we go. And we've got our answer. Right? So once we get to that z-value point, it's the exact same stuff we were doing before, right? In fact, other than like step 1 and 2 here, this is all the same stuff that we had in a previous problem, right? So kind of what it hinges on is knowing that these sample means will be normally distributed around whatever the original population mean was, and their standard deviation or their variance will follow that equation where the variance of the sample means is the original variance of the data we sampled from divided by our sample size. Okay. Any questions on that? Hopefully we're kind of seeing, kind of connecting this to stuff we've talked about and adding some additional stuff about sampling. I think I'll say this. Maybe we'll start out kind of working. Actually, I'm going to put up, just to kind of see, if we're going to get some practice with it. I'll put up an online quiz on Canvas today. It'll be due before we start class on Friday. It'll probably have just a couple questions, kind of like this, where I'm giving you kind of some population mean, population variances, having you kind of work through some of these problems. Just to kind of see, even after this very short introduction, kind of how we're grasping this, and then kind of I'll probably use that information to see like how much time we should spend on this on Friday. Kind of take a quick look at that before we start class. And then we'll probably go through a few questions, regardless of how you guys do on that little quiz. And we'll jump into how do we do this not only with sample means, but sample proportions. We can then start to kind of move into these things called confidence intervals, which is pretty interesting. So one thing I was going to, I think I mentioned I was going to tell you guys about this. I just thought it's interesting. Sometimes I see things, first of all, any questions for it and kind of end things here. Okay. So I always think about, when I see things, I try to think about how maybe it relates to stuff we've talked about in class. And I see these online, all these apps where you can like bet in sports, different sporting events. And they offer like all these boosts. I always think about like, how are these companies making money, right? Right, because these bets are supposed to be like 50-50, so they should be making, they take a cut. But one thing that they do is they try to offer these boosts for different events that happen within the same game. And I've really noticed is if you actually work out the numbers, they'll say something like, take this bet, it's boosted up to better odds, but it's, the probability that some running back gets over a certain amount of yards, but also that the quarterback gets over a certain number of yards. Well, the kind of interesting thing you can think about is that, okay, so you're thinking about what's the probability that, you could do either one, right? So what's the probability that A happens or B happens, right? You can kind of take both of these, and one thing that we talked about was the union of two events is going to be the sum of those events, but also if you subtract out the intersection. So I kind of keep a little bit of an eye on this, but they'll offer these two outcomes that they know are related to each other or that they know aren't mutually exclusive and that there is some intersection. And then if you work out the odds, they'll give you basically the odds is if you just added the probability of both of those things occurring up without kind of subtracting that intersection. All right. So this isn't necessarily just apply to sports gambling. You see this kind of in different things casinos do or anything where they're offering odds. A lot of the times they will rely on the fact that people don't understand that this happening or this happening is not just the probability of both events added up, but you also have to think about the probability that both of them occur, right? Or subtract out that intersection. So that's something we talked about a while ago, but you kind of see it pop up. It's just one thing I saw kind of in the real world. And so I always try to kind of relate things or kind of mention things that we've done, kind of how we see that play out. Okay. So I've kept you guys over a little bit. So I'll let you get out of here. Start working on that individual assignment. If you have questions, like I said, I'll be around my office 2 to 4 today as well tomorrow. If those times don't work, shoot me an email. We can try to figure out another time to meet up. See you guys on Friday.